Good morning, my dear students. This is the first class I am taking for you regarding the subject discrete mathematical structure. Myself, Dr. P.V. Mutare GSI, professor in mathematics, want to conduct the class for you from the model number 2 after Rajeshwari Madam's class on the previous model. What is the mathematical induction? We can know from this PPT that you might have seen the word mathematical induction in the first PU in your PUC classes. What is that? If any procedure, if any theorem we want to prove, what we are doing, what we have to do by the mathematical induction procedure, take n equal to 1, n equal to k and n equal to k plus 1. If all the three conditions are satisfied, then you can say that the theorem is proved by mathematical induction. The same is showing here. Let S of n is true for n is equal to 1 or S of 1 is true, I mean n equal to 1. If S of n is true for n equal to k, that is z plus is what? Set of all positive integers, then S of n plus 1 is also true. This means what? If we put n is equal to k, if we put n is equal to n plus 1, if both the conditions are same, then we can say that the theorem is proved by mathematical induction. Using that fact, let me take one simple procedure. Before that, we shall go with working procedure for the theorems. What is the step 1? We verify the theorem for S of 1, I mean n equal to 1, which is true. That is, it should satisfy. Next step is, we assume that S of n is true for an arbitrary integer k is greater than or is equal to 1. That is, for other than n, you can take. Here, let me take it by, denote it by k. Rewriting S of n, replacing n by k, that is putting n is equal to k. Starting from the step, we show that S of k plus 1 is also true. Here S of n is true. If S of n is true, then S of k plus 1 is also true. This is the working procedure for our problems as I discussed in the previous T. Let me take one simple theorem. Prove the following statement by mathematical induction. The statement will be 1 plus r square plus and so on r raised to n minus 1 is equal to 1 minus r raised to n divided by 1 minus r, where n is greater than or is equal to 1, where r is not equal to 1 and n is a positive integer. What are the numbers this ratio, I mean the series indicates? What is r here? R is the common ratio. 1 plus r, instead of 1 I can make it r raised to 0, r raised to 0. Therefore, r raised to 0 plus r raised to 1 plus r raised to 2 plus and so on r raised to n minus 1 up to n minus 1. If you add these terms, this is called what? R is the common ratio, hence the numbers are in the geometrical series. And their sum is given by 1 minus r raised to n divided by 1 minus r, where n is a greater than or is equal to 1, I mean again it's a positive integer. R is not equal to 1 because the denominator, if you put r is equal to 1, what happens? The denominator becomes 0, which becomes infinity, and n belongs to z plus. Z plus is what? It is again a set of all positive integers. Yes, write the theorem, I mean the statement in this manner. Go according to the stepwise procedure as we have discussed here. S of 1, put r is equal to 1, LHS, put r is equal to 1 here. What happens? 1 raised to 1 minus 1, that is 1 raised to 0, that is 1. LHS is 1. Then come to RHS. R is equal to 1 is what? 1 minus r divided by 1 minus r, which is equal to 1. Therefore, if LHS equal to RHS, then S of 1 is true. Go to next step. We shall assume that S of n is true for n is equal to k. As we have already known that, we shall prove the theorem for n is equal to k also. It means what? Wherever there is n, put n is equal to k. That's all. There is no change. Remaining terms will be same. Call the theorem by 1. We shall add the term r raised to k onto both sides of 1. here. Now you can put a question, sir, why we need to add r raised to k? Because you might already shown s of k plus 1 is true. Here just observe that. What is the relation between s of n and s of n plus 1? If s of n is the nth term, s of n plus 1 is what? It's the next term. Therefore, we need to add its next term. Here the term is r raised to k plus 1. Its next term is what? Which is 1. That term will be r raised to k. Therefore, we need to add r raised to k. Keep in your mind that we need to add next term in this series. Next term in this series on both sides. Observe here, r raised to k minus 1 plus r raised to k in the left side. In the right side, 1 minus r raised to k divided by 1 minus r plus r raised to k. Taking the LCM and so on, it will be 1 minus r raised to k plus 1 divided by 1 minus r. Call this term is theorem number 2. No, sorry, result number 2. Yes, result number 1 is already here. Result number is already 2. What is the difference between these two? Just observe. 1 is there, no change. R is there, no change. Wherever there is k in the result number 1, what is the implication? K is replaced by k plus 1. Therefore, s of n is replaced by s of k plus 1. That is n is equal to k again. That is k plus 1. S of n is equal to s of n plus 1. Therefore, wherever there is k in the first equation, I mean the result, that k is replaced by k plus 1. Comparing 1 and 2, we can conclude that s of k plus 1 is also true. What is the third step, second step given here? If s of n is true for an arbitrary integer, then s of n plus 1 is also true. The same procedure we are getting at the end. Hence, by the mathematical induction, for all, set up all integers 1 plus r square and so on, r raised to n minus 1 is true for n is greater than or is equal to 1 when r is not equal to 1. Similarly, come for the next theorem in the series. 1 plus 2 plus 3. What is the term? It will be sum of all natural numbers. What is the natural number? N into n plus 1 divided by 2. You might already know. The same procedure we are implicating here. LHS equal to 1 because n is equal to 1. RHS equal to 1. 1 into 1 plus 1 divided by 2. Again it is 1. Therefore, LHS is RHS. Therefore, S of 1 is 2. Next, go to the step 2 as we have seen in the previous theorem. Therefore, n is equal to k. Put n is equal to k. Then add is to next term in the left side. What is the term here? K. What is the next term? K plus 1. Therefore, we are adding k plus 1 on both sides. Refer here. Here in the left side. Here in the right side. Therefore, take the right side LCM in the right side terms. It will be k plus 1 upon 2 into k plus 1 plus 1. That is k plus 1 upon 2 is same thing. K plus 2 can be written as a k plus 1 plus 1. Why this is necessary? It's a very simple one. We need to compare results between 1 and 2. We need to compare the results between 1 and 2. It means what? Wherever there is k, that k is replaced by k plus 1. Observe here. Am I correct? Yes. This is the procedure, I mean the conclusion to prove the theorem by mathematical induction. In the next classes also, we need to go for some of the theorems based on the same procedure. In the examination also, do not jump some of the steps. You need to write all the steps in a clear manner so that you can have the clear knowledge about this mathematical induction. It has a very wide application in proving the theorems. In the next classes, you can know how it will be effectively used to prove the theorems which are not possible to prove by our traditional methods. That's why the procedure of mathematical induction is using here. Okay, thank you. Yes. ಇದನ್ನ ಕಂಟಿನ್ಯೂ ಮಾಡ್ತೇನೆ.